we will write code to create a mobile robot in URDF using XML. So for starting to create a URDF file, let me create a directory folder for my workspace. So mkdir. So before it, I have already installed ROS 2 Humble distribution. In my system is like Ubuntu 22.04, and I have installed Gazebo, and I have already installed ROS 2 Humble. So I'm creating a folder for this tutorial. So ROS 2 workspace. So I'm creating ROS 2 workspace. So let me enter in the workspace. So here there is no file. So now I have to create a URDF file. So let me create touch. Give any name. I can give my robot dot you can give mobile robot because I'm going to create mobile. Any name you can give based on your own choice. So URDF. So you have to write like this. Now I have already created a URDF file. So now I am going to write everything in this URDF file. So for writing, I'm opening my VS Code. So code space, I can enter. So here I can see my mobile robot.urdf is present. So first let me start with the tag, opening tag and closing tag, because I'm going to build a robot. So I'm writing robot and the name of the robot. So name, we have to provide name. Let's write any name. My robot, you can write any name. My robot or mobile robot also you can give. Okay, then close this tag. Okay, so after closing it, like whatever things you will write should be within robot tag. So in robot we will have two things. First one will be the link, various link, and for connecting one link to another link we will use join. So for writing link we have to again write link closing bracket, then we have to give the name of the link. So first link is the base link. I'm going to create base link. So now I have to close it also. Inside the base link I have to write everything. So now like in robot description file, we have to write inside a link we have to write like three property of the link. What will be the three property? First will be the visual properties, second one will be the collision properties, third one will be the inertial properties. We can search it on Google also how to write a link. So if I will open a Google, we can see URDF XML. So here this is the official page of the writing XML specification. So here for writing a link you can open it. So here you can see this is the link, this is the joint we use to connect one link to another link, and we have to provide collision property and we have to provide the inertial property, and using visual property we can see the link. So in link we have to write elements. So inertial we have to write, and within inertial we have to write origin, inertia and mass, and in visual we have to write name, geometry. Name is optional, so geometry is required. So in geometry we can write box. If we are using box type of geometry, we have to provide size. So size means what is the length, what is the width, what is the height of the object, means box. And then if we are using cylinder, then we have to provide radius and length, and in case of sphere we have to provide radius. and in the same session we have to also write like material like this. Material, in material we can provide color of the link. So this is the basics. So here let's start writing link. So inside the link, first property I'm going to write visual. So visual, okay, and then closing bracket for the visual. Inside visual we have to write geometry, origin, and material. So first I'm writing geometry, close it, and then close it, closing bracket, geometry. So inside of geometry we have to write like for the base link I'm going to use box. So I'm using opening tab, box, and what is the size of the box. So we have to enter in double quote. So I'm giving like length as a 0.6 means 60 centimeter, 0.4 as a width 40 centimeter, and 0.2 as a like height I'm giving. And I have to close this box, box tag also. Okay, so like this we have to close. And also if you are not interested like this, closing like this, so you can write like this also, box. Okay, this is also correct. And for saving time you can also direct instead of writing like this, you can directly use like forward slash and remove it. This is also like a closing bracket. Now after writing it, we have to write down the origin. In origin we have to write XYZ position. So initially I am giving 0 0 0, and then roll pitch here. So in roll pitch here also I am giving 0 0 0, and we have to close it. And then after we have to write another thing is material, because if you will not write material property, then there will be like all the links will be in the same color. So I'm writing material also, material. So within material we can give the name. Let's assume I'm giving a name as a green. I'm giving green. Any color you can, based on your choice, you can write it here. Then material, and inside material we have to write color RGBA. So RGB, red, green, blue, and A will tell you the transparency of the object. So I'm giving like green. So 0, red 0, green 1, black 0, and transparent. Yeah, it should be visible. So I'm closing it. Now my base link is prepared. So because this is first time I'm writing, so I have to check whether there is any mistake or not. So for it I have to visualize it. So I'm opening my Terminator. So here I have to write like ROS to launch. So I'm using launch file. You can also create your own launch file once you will have a good level of understanding of ROS to how to run a node and these things. Then you can also create your launch file. Right now I'm using a launch file provided by the ROS2 and in the package of URDF tutorial. So I'm after writing half words, I'm using tab so to complete it. And in this package, like after ROS to launch, URDF tutorial is a package. In this package we have a file name as a display.launch.py. so this is the convention of writing a launch file. It is a Python file. Basically it is a Python file, but we use a .launch also to identify it as a launch file. So again it's a Python file completely. So then we have to pass the argument, because they have written this launch file for their own URDF, but here we are creating our URDF file. So we have to pass that file as an argument. So I'm passing model colon equals to name of the file. So I have to give the path of the this file. So this file is in home dr and ROS to workspace, and then mobile robot.udf. Then we have to enter, and we can see here we can visualize our robot in RViz. So when we are like launching a launch file, two nodes will be active. One node will be the robot state publisher. In robot state publisher we will see all the joints, like later we will also discuss about the joint state publisher, and another will be the robot state publisher. So in robot here you can see this is our base of the robot, and now we can visualize it. So here you can see this box is half inside, half above side of the surface. It's not properly on the surface. You can see here surface is like we have to, in x direction we have to give some, like we have to shift this box in z direction. So let me write, cancel it, and then again in z direction we have to give, because half in z direction 0.15, we have to place it in 0.15, because total height is 0.2, so we have to pass 0.1. Now we can see our robot again. So if I will run again, so yes, now we can see our base is on the surface. Okay, so now we have to provide another link name as a wheel. So now we have to give a right wheel, left wheel, and caster wheel to make it complete robot. So before giving the link, I want to give the collision property also, and collision properties and inertial properties also for each link. So after writing visual parts, remember collision properties. If we will not write collision properties, then one element, one link can collide very easily, can pass another link without any constraint. So that's why we have to provide the collision property also. So I'm writing collision. So in collision we have to closing bracket, and then I'm writing collision. So within collision we have to pass two things. First one is geometry, second one is origin. So I'm copying it from here simply, and then I can pass it here. And then third thing is we have to pass inertial properties also. So inertial properties we have to pass, because if you will not pass the inertial property, then your robot will not be visible in Gazebo. In RViz you can visualize your robot, but for Gazebo, when you will like import your robot in Gazebo, so it will not visible if you will not provide the inertial properties. So that's why I have to write the inertial properties also. So in inertial properties we have to calculate like inertia for this object. So first I'm writing like origin we have to use as it is. So here also we have to pass three things: origin, mass, and inertia. In inertial, like we have to pass like this, and then mass, opening bracket, mass value will be I have already defined like mass weight for mass for the this one, like let's assume 5 kg I'm giving mass for the 5 kg for this object. And for the inertia we have to calculate the inertia matrix for this object. So if I will open on a Google list of moment of inertia. So here we can see So for like list of moment of inertia, if I will write, so I will check. And for the solid like 3D inertia tensor, so we can see the matrix here. So for cube, solid cuboid, we can see the inertia matrix is here, like 1/12 m and height plus depth. And this is the inertia matrix we have to calculate for the cuboid. For the sphere also we have inertia matrix. For the cylinder also we have the inertia matrix, like a solid cylinder we have the inertia matrix. So in case of wheel we will use solid cylinder. So here we have to calculate the inertia matrix. We know mass, we know length, like length, width and height we know already. So we have to put the value in this equation and we have to calculate it. So for making it easy, like I have already calculated it. If you will use, like later if you will have a good experience in URDF and you are using Jacro, then you can directly define these like variable, and you can pass value of mass and everything. But if you are using only simple URDF, not using Jacro, then you have to calculate these value and you have to pass it. So here I have written already, calculated here already for inertia. So here we can see for the base link I have already calculated. So I have calculated, like here I want to show you another thing. So here we can see in inertial properties in collision, in case of inertia, the inertia matrix is a symmetrical matrix. So here you can see the inner 3x3 rotational inertia matrix is specified with the inertia element. So because this is the symmetrical matrix, so we have to pass only the 6 element, not all 9 element of the matrix. So we have to pass IXS, IYY, IXZ, IYY and IYZ and IZZ. So here in list of the moment of inertia we have, like in solid cuboid we have 9 element, but we have to pass only the upper triangular matrix part. So that's why I'm going to write only these 6 element in inertia tag. So in inertia tag here you can see inertia tag, you have to pass IXS, IXY, only the 6 element. Okay, so first you have to calculate it using calculator and anything, and then you have to put the value directly here. Okay, and like origin for the inertial property is optional, but I have already also written, no issue. And then you have to pass the mass value. Mass value is compulsory. So I have already calculated, so I'm going to copy it. So because I'm using mass less 5 kg, and in case of like 5 kg, so that's why for avoiding the sliding I multiplied each value by 4. After calculating the actual inertia matrix, I multiplied 4. If you are not interested to multiply with any value, then you have to increase the value of the mass. Instead of, if you are taking 5 kg only, then I observed my robot was sliding slowly. So that's why I have multiplied it with 4. And for avoiding such kind of things, you have to increase the value of the mass. Like instead of 5, you can use 10 kg for the box. Okay, so this is the inertia properties we have to write. And now we have completed all the things. So we have written the visual properties, we have written the collision properties, we have written the inertial properties completely. Now I want to check it once again whether everything is correct or not. So let me run again. So it's not visual, so like there is some error. So what is the base link? So because I have written the inertial properties, so I have to write base link also. So because I have written here, I have to close it. So here come to here. So here I have to write like, because only I have only written one link. So then it is asking for the, it is confusing between like base link, what is the base link. So I have to write another link, then also I will provide the base link and all. So for second link I'm going to write link. Everything is correct, no need to worry. Like once I will write the second link, we can see all the things. So, link, second link is name, and then we have to pass the second link name, right will link. So in right will link, again we have to pass opening closing bracket and link, and then we have to pass other properties like the way we have written right now. So visual, in visual, and then closing tag of the visual. Okay, visual. Okay, inside the visual we have to write again we have to write our geometry part, and then geometry part. So in geometry I'm going to use cylinder radius is equals to 0.1, and then length is equals to, I'm using 0.05 centimeter. Okay, close it, and then we have to write origin. Initially I'm using origin we have to initially I'm using xyz equals to 0, and then roll pitch here also I'm using 0, 0, 0. Close it, and then after I'm using material also. Material name we can pass gray, any name you can give. Then closing bracket for the material. Now I'm passing the color. In color we have to write like RGBA. So I'm using gray, so we can give 0.5, 0.5, 0.5 and 1 for visibility, and then that's it. So I've written two link. Now what is the relation, like we have to write the joint to define which link is parent, which link is the child. So I have to write join, first join name is equals to, I'm giving base right will joint, and type of the joint, because we have to make wheel rotating continuously, so type we have to place it here continuous. Okay, so joint, and then closing tag for the joint. Then now we have to write like within joint we have to write parent link is the base link. Close it, and then child link is equals to right wheel link. Okay, close it. Now we have to pass the connection plane origin. So origin I'm passing xyz initially as a 0, 0, 0, and then later we will decide the exact. Roll pitch here also as a 0, 0, 0. So passing it, and then axis of the rotation, because it's a continuous means rotating, then we have to pass axis. So I'm passing axis x, y, z. Initially I'm placing it randomly. Let's assume about the x-axis 0 0 0 and close it like this. Okay, so I have already written like now I have written the second link. Now we have to visualize if there will be a problem. So then now we will we will close comment this collision and inertial properties. Later we will open it. So I'm going to run it again. So let me run. So yes, we can see it here, the wheel. So let me close it. For now I have to close it, and later we will open it again. Let me comment it. Okay, 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 just here. Okay, so we will see later. I will open it again. Maybe there is just some problem. So let me open. So we can see now our base robot is here, and wheel of the robot is also here. So now we have to. So here red one is representing the x direction, and green one is representing the y direction, and blue one is representing the z direction, and this one arrow is showing like child parent relationship. So this one is the parent and this one is the child. So now our goal is to place wheel here this side. So we have to in negative y direction. So here you can see this one is the positive y direction, negative y direction. We have to shift half of the width. Total width is 0.4, and then we have to shift half of the width, and then here I have to write 0 point. So let me visualize everything. Bigger, so that it will be easier for you to see. So here, so in joint we have to give here in negative half of the width. So in negative direction minus 0.2. If I will place it here, and then if I will run again the command, if I will run the command, so you can see now robot is here. Now we have to rotate the wheel about the which direction, about the x direction. With respect to x direction we have to rotate 90 degree. So 90 degree we have to rotate. So I have to write here 90 degree. So here if I will rotate 90 degree here in roll pitch, 180 degree, 180 degree is like pi is 180 degree. So half of the pi, like 3.14 is the pi, so half of 3.14 is 1.57, approximately 1.57. If I will write here 1.57, then it will rotate the axis, not the wheel. Sorry, it will rotate the axis. So here we can see, if I will place it here, and then yes, but it's rotated, like wheel is rotated, but axis is also rotated, because z direction blue one should be upside. If I will disable it, so axis is also rotated. So our goal is like axis should be same as the parent. So for avoiding these things, I have to rotate the, I have to change in, not here, I have to write it 0, and in the link origin here I have to write 1.57. If I will write 1.57 here, and then if I will run it again, so we can see correctly placed. Okay, so now we can see the axis, we can see the axis of the both wheel and base is same direction. So now again again you can see here half of the wheel is again still inside of the base robot. So we have to, so like half of the, what is the length of the wheel? Length of the wheel is 0.5 I have given. So half of the 0.5, 0.025. So I have to add it in z direction. Where is the joint? In joint here 0.025. okay, I have to add it and then again run it, and then we can see here wheel is completely separate from the base. So like this we have to create the left link also. So I'm going to just copy it. So for the link parameter will be the same, just instead of right wheel we have collision and inertial properties we will write later. So here I am writing the same because other properties will be the same. So here name, left wheel, link, radius and other things will be the same, and then we have to define the joint also. So I'm going to write, copy it and then paste it here. Instead of right, here I have to place left. And one more thing, like now we have to place the wheel we have to shift in y direction, but it should be positive instead of negative. So like this we have to write, and then here link name is not right wheel link, here link name is left wheel link. Save it, and then again I can run the command. So here we can see both the wheel are available, and if I will disable it, so we can see like parent for the both is the base link, and axis of the both wheel is in same direction, z is like upward, red one is representing x. Now I will enable it again. Now we have to one more important thing, like joint state publisher. In joint state publisher, because we have given like continuous joint, so it will rotate. So I have written the rotation about the let's x-axis. So here in right left wheel, so see it's rotating about the x-axis, but we have to rotate about the y-axis. So here we can write again here instead of axis x we have to write y. For this one also 0 and 1. okay, so now if I will run it again, so we can see our robot is ready. So if I will rotate using joint state publisher, so it is rotating perfectly. Okay, so like this we have to write. Now the third wheel is the caster wheel. So again I'm not writing the physical properties, I will write very soon once I will complete it. So for the caster wheel, again I am copying it from here, link name. Okay, so here instead of left wheel I am writing caster wheel link. So in caster wheel we are I am passing like a sphere. So in sphere we have to give only radius. So I'm like 505. okay, and then initially I'm passing like there is no need to give here 90 degree, and initially I'm passing like 0 0 0. Okay, caster wheel and other things are correct. So joint name also I'm copying it from here. Instead of left wheel, caster wheel joint, and type will be fixed. Now parent is in the base and child is the caster wheel. And let me initially give the 0 0 0. Later we will decide like what will be the exact. And because it's a fixed, type is fixed, so no need to pass the axis. So save it, and we can see now our robot. So here we can see wheel, like caster wheel is here, right wheel and left wheel, and base robot is here. So now we have to place this caster wheel somewhere here, not at the center, to maintain the balance. So I'm going to pass it like in x direction, positive x direction. We have to shift it like 0.2 I'm passing. So here in caster, positive x direction, because this one is up here, like from center to corner, no, total length is 0.3, so I'm passing 0.2, and also like our goal is to right now caster wheel is half inside of the box, so we have to shift it like below the box. So we in z direction we have to write we can say like radius of the sphere. So in z direction 0.05, we will check and then we will decide. Okay, so like okay, minus, so in negative direction, so I have written in positive. So because we have to place this caster in negative z direction, so here we have to place it minus also. So now we can visualize it again. Yes, so now we can see perfectly, right? So here another one problem is like right now our base link is also on the surface, whereas wheel is also like touching the inside the surface. So we have to write a reference base link. So here I am going to write another link. Okay, so this is the last link I am writing, reference, and okay, link empty, it's an empty link, like name as a reference link. Okay, I'm not passing anything, so it's an empty link, complete. So I have written only name and it's empty link. So I can write here like this: joint name is equals to base reference joint, and type giving fixed, and then we have to pass joint again, and inside joint we have to pass parent link is equals to reference link, and then child link we have to pass base link. Okay, close it, and then origin xyz is equals to 0 0, and in z direction 0.5. We will check it soon. So let me put it 0 here initially, and then roll pitch here, and value will be 0 0 0. Okay, so okay, so here if I will run it again, there will be we will not see any changes because I have not given in x direction, z direction, so I have to write the z direction also. So basically uh, here here we can see we have to give the joint like 0.05 radius of the sphere. Okay, so I'm giving like here z direction 0.05 and positive the reference length is 0. Okay, let me check and then we will correct it. Okay, okay, I run it again. So still it is on surface, so we have to change it from global option. Here from base link, instead of base link I have to use reference link, and then yes, we can see now now it is like above the surface. Base link is the above the surface. Okay, so we can see here this is like if I will disable the robot model, so we can see everything is like here. Yeah, like and this is the base link, left wheel, right wheel, caster wheel, and this is the reference link. Okay, so like this we have to create. So I have already created our robot. Now we have to pass the physical properties also, as I have discussed in the first part. So I'm going to write physical properties, and so physical properties we have to write inside the like link. So I'm enabling it: collision, inertial, okay, inertia. So again we have to write collision for this link, collision, and we have to close it, collision. Okay, and then in collision we have to pass the geometric and origin. Okay, and then after collision we have to write after collision we have to write inertial property, and okay, inertial property, and inside inertial properties origin is optional, and we can pass origin also. Mass and inertia is compulsory, so we have to write mass value is equals to 1 kg in case of wheel I'm passing. Okay, and then inertia I have already calculated, so I will use directly from here. So cylinder, in case of cylinder I have written here the value. Okay, because property is same, so I'm using like from here. Okay, copy it, and then I'm placing it here. So okay, so like this. Okay, then for this one also, and closing bracket for the inertia. Now in the same way we have to write for the left wheel also. So I think for left wheel also everything is the same, so I'm going to copy it from here, collision and inertia. So directly I can put it, here. And then last one is the caster wheel. So in case of caster wheel we have to write collision, close it, collision. Inside the closing bracket we have to pass again geometry and origin. Okay, and then outside of the collision we have to write inertial properties, inertial, closing, inertial. So now inside the inertial we have to pass origin. Origin is again optional, you can if you want to skip you can skip. And then we have to pass the mass is compulsory, you have to pass. Value I'm giving 0.5, so in double quotes 0.5. okay, close it. And then inertia I have to write, last one, inertia. So again I have to copy it from here, I have already calculated inertia, so I can copy it from here. Okay, so like this. So like this we have to write. Okay, so close it. Now I'm going to run it. Our code now, okay, so now we can see our robot is ready. Now we have physical properties as well as inertial properties also we have, and we have visual properties also. So if I will, like in global option, if I will enable, instead of base link, if I will enable reference link, so we can see our like base is above the surface, so it's ready to move. So for moving these wheels we have to add we have to add some plugins, differential drive plugins. So in Gazebo there are many plugins, so we can use directly. So Gazebo ROS plugin packages we have to check. And here in Gazebo ROS packages, you can say the Neotic, but we have to open ROS 2. So in ROS 2 we have Gazebo plugins. So here in Gazebo plugin include Gazebo plugins. Here we can see different types of plugins is already available. We have to copy it and paste it in our URDF file. So for I'm going to copy it the differential drive, because my goal is to move the wheel. And if you are using camera you can use this plugin. If you are using bumper you can use this. So for the various sensor also you can get the plugin from here. So I'm using differential drive plugin. So here in differential drive plugin, here from here, so let me copy it, and then till here I have to copy it, and then I have to place it in my URDF file. So I have to open a tag for Gazebo. Remember Gazebo should be installed in your ROS, and then I have to place it. So first let me correct it. Okay, and then this plugin will be here, and then this should be like this. Yes, no, it's correct. Yes. So now I'm not going to use this one, so delete it. So update rate should be there, update rate frequency should be there, and left wheel, right wheel, kinematics, I'm not going to write the kinematics and limit, so I'm removing it. Okay, CMD velocity, so input is CMD velocity and ODM, so these things. So let me write the name, mobile robot my mobile robot name is mobile, or you can write any name here, but file name should be the same. You cannot change the file name. If you will change, there will be a problem. And here in the left joint I have to put the left joint. So for the left joint, this one is the right base left joint, this one is the left joint, so I have to place it here, left joint. And then for the right joint, name in the base right joint, right wheel joint. Okay, I have to put it here. Fortunately our input is CMD velocity and we have to odometry, we have to keep it as a true. And then one more thing, okay, odometry chassis. In chassis we have to pass a reference link instead of base link. Reference link. One more command I have deleted, so I have to write this one, kinematics, wheel separation. So we have to write wheel separation, kinematics, wheel diameter, we have to write the kinematics. Okay, so here after this I have to write okay, wheel separation. What is the separation between wheel? So here we can see the separation. So total width of the base, and then like half of this wheel, means diameter of the wheel, not diameter, length of the wheel. What is the length of the wheel? We have written length of 0.5 0.1. Length of the wheel I have written here. What is the length of the wheel? Length 0.5. so I have to add here. So wheel separation 0.4 width of the base and 0.5. okay, let me check again for confirming it. So this one is the 0.4 from this wheel to this wheel, and half of right wheel and half of the left wheel, so total will be 0.5. so I have to write 0.4 plus 0.05, so here it will be not 0.05, 0.45. okay, and wheel diameter, what is the wheel diameter? So we have to write wheel diameter is radius is 0.1, wheel diameter will be 0.2. Now our robot is ready. Everything we have already written. Now we have to import this robot in Gazebo. I'm going to run it from here. First I have to check whether everything is working well or not. So ROS to launch and URDF tutorial and then display dot py model is equals to because I have to give the global path home and ROS to workspace and mobile robot dot URDF. So we can see like everything is working here, and we can visualize our robot like base link in form of green color and wheels in form of gray color. So we can see that everything is like wheel is rotating well, both the wheel are rotating well, and caster wheel we have provided like fixed type of joint, so it will slide on the surface. So we will provide the friction coefficient also for the caster wheel. So like now our robot is ready, and we can see if I will disable it, so we can see let me center everything. So we can see our like TF transform, and again blue one is representing the Z direction. So now our robot is ready to we are ready to insert our robot in Gazebo. So in the next step I am going to import robot in Gazebo. So let me clear it. So we have to write the command ROS to run robot state publisher, and then ROS args argument. We have to pass argument like robot. We have to write robot descriptions here, right? Description, and then we have to write in this way. Okay, and cat and file name is mobile robot.urdf. we have to enter. Now this node is like active, and now we have to open Gazebo. ROS to launch Gazebo, ROS Gazebo launch py. So we have to run our Gazebo also. So yes, Gazebo is now open. So third one is we have to spawn our robot. We have to import our robot in this Gazebo environment. So I'm setting it so that we can visualize easily. So yes, so I have to write here ROS to run Gazebo ROS spawn entity dot py, and then we have to pass topic name is robot description, and then entity, and in entity name of the robot I have given my robot. So then we have to enter. Yes, now successfully spawned entity my robot is here. Now actually we are saying like in gray color, because in Gazebo that material property does not work. We have to give property in form of Gazebo. So for color we will provide color also, and before that now we are going to run this robot. So we have to check like we have to type the command ROS to let me check the topic list. So here important topic list is through which we can send the velocity command velocity, and in plugin also I have written like command velocity as our input. So we have to pass the command velocity. So I'm going to write ROS to topic and we have to publish cmd command velocity, and then geometry type geometry message, and message is twist, and then I have to pass the message, so double quotes, and then curly braces, and then we have to pass linear velocity, linear because I'm going to pass linear in because my mobile is going to run in x direction only, so I'm passing linear velocity x. I'm not going to pass the y and z because this robot will run in x direction, so I'm passing 0.5. so and for angular and angular we this robot can rotate with respect to z axis, so we have to pass z axis. Initially I am giving 0 angular velocity, and we have to see. So now this robot starts running. So now robot is running, and meantime if I can change the velocity, so okay, so I can give like 0.8. so angular velocity I am also giving, so we can see this robot is now turning, and I can pass another like again 0.0, so that it will move in the same direction. So now we can see here this robot is showing like very absurd kind of behavior. So because because this wheel, caster wheel, is the fixed wheel, so we have to provide the inner friction properties also. So I have to define mu1 mu2. So before that I have to stop it. Okay, let me stop. Okay, so now here I have to write caster wheel property. So here I have to write mu1 and mu2. So for the velocity I have like gazebo. In gazebo we have to pass reference. In reference we have to write name caster wheel link, and close it. And right now I'm going to give the color also, so that we can see the different color. Okay, gazebo, close it. So here color, in color I have to write like first I have to provide friction value mu1. Let me give the value as 0.1, and for mu2 also value as 0.1. I'm giving 0.1, give it 0.2. Up to you. And also I'm going to write the material. So material. So in material tag we have to write gazebo, and then color as a gray. Close this tag. Material. In this way I have to write for each one. So I'm going to copy it for all the link. We have to provide not mu1 mu2, only the material, so that we can see the exact color also. Okay, so I'm writing. Okay, so first one is the base link. Base link. So base link is the green, and then right wheel link. Right wheel is the gray, and then left wheel link. Like this we have to write. So now we have to start again our code. So I have to run it. First step should be followed. First we have to start the robot state publisher. Like first robot state publisher we have to start, and then after we have to start Gazebo, launch the Gazebo. And now I'm going to import it. Now we can see our robot is here in the color also, and then we can pass the velocity. So I'm giving initially like 0.5 velocity also. So first time it will give like some. Now you can see now it is moving smoothly instead of having a lot of jump kind of thing. So like this we can create our robot, and we can make our we can import in the Gazebo environment. We can see our robot is ready here, but instead of giving like open environment, I'm going to construct some. I'm thinking to add some obstacle also, so that in future we can we can provide algorithm for obstacle avoidance and other things, and it should follow. So for creating a environment in Gazebo, we have to type here beside in world there is option as a insert. So in insert we will see we have to wait for a moment because it's connecting to it's connecting. So once here will robot model it's connecting to the database. Once we will see like model is already here. So now from model we can add any kind of things. So like let's assume I'm thinking to add a beer, so we can see a beer here in this environment, beer bottle. And if I want to book save, so I can place a book safe also. Okay, like this. And if I want to create a bowl, so I can place a bowl here also, and like this we can create. And also if I want to make a wall, so let me create a wall building editor. So click on the edit, like add path, click on the edit, and here you will see like build editor. So here in build editor we can see whatever things we will do here. We can see as a wall here also. So I'm going to draw a wall. So let me draw like this. Okay, so okay, now again from here I'm going to add wall, and then I'm going to move it like this, and then okay, and then like this. Okay, so I have created a wall for my robot. Okay, now I can provide the window door also. So let me give a door here. Okay, one door, and here, and some windows we can give window. And if you are creating a multiple floor environment, then there will be stairs and others also, and we can provide the roof like this. We can use and we can style also. Okay, and we can do so like this. You can create your world. So I'm going to save it. Before ending, save it as my world. My world. Okay, so save it. Now I have to exit from here. Exit from builder. Are you sure? Yes. Now we can see. So here my world is already available as a path. So now if I will give the command to run this robot, so we can drag and drop anywhere in this environment. Okay, so if I will give command now, let's see. If I will give a command to run this robot, then this should not, because we have given collision properties, so this robot is not going to pass this wall. So here I have to pass command line, and if I will give instead of 0.9, because 0.9 will be very fast, so 0.5 if I am passing, and 0. So now okay. 0.5 I am passing. So now robot starts moving. So now like yes, so for the wall we can see it cannot pass to the wall. Okay, so now it's stuck here, but we can see wheels are moving. It's not visible, but because the we can visualize. If I will pass the speed very high, so we can visualize like the robot is moving very fast. If I will see, you can see robot is sliding, moving, but due to the wall. Okay, again I am doing same mistake. So I will fast 9. So we can see here wheel is rotating very fast. Okay, but due to the wall it cannot pass the wall. So I have to pass negative velocity also. So here if I will pass negative, so okay, so not here. Here if I have to pass negative velocity, so robot is moving back. Okay, robot is moving. That's it, and we can